Hi guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at one of the applications of motion in two dimensions, and this is going to be one of the, of course, problems at which that promised in our first video. So we had looked extensively into the concept of vectors, which of course are going to assist us in trying to depict various forces and velocities which are going to be involved in motion in two dimension. And I said that of course for a problem that is going to involve motion in a plane, this is going to be a pair of a one-dimension motion, as we're going to be showing from that specific graph of A and B. And that is going to be giving us, in a sense, of one of the implications of motion in two dimension in terms of position, velocity, and acceleration. And this is going to be achieved by a representation of various vector components, which had, of course, shown from our previous discussion. So in this case, we're going to consider the aspect of instantaneous velocity, whereby we're going to use the lower example. So in this case, for the graph 2, this is going to be an example of a car which is going to be moving from a point that I'm going to give as 1 to the point 2. And this is going to be moving along this curve, which is an oval curve at a velocity of 30 meters per second. So in this case, this is going to be a car that is going to be moving around an oval racetrack at a constant speed of 30 meters per second. So in this case, we are going to be required to evaluate the instantaneous velocity of this specific car. And of course, we are going to be finding this specific aspect of velocity. So let's give this one as instantaneous velocity at point 1 and 2. So I'm going to give this one in that summary form because of our space. So we're going to be required to find the instantaneous velocity at 1 and 2. And therefore, we are also going to be required to evaluate perhaps at the time or the time it's going to take, or the average velocity for the car during this specific time interval. So in this case, we are going to be giving additional information that the time difference this specific car takes, or the time taken, is equivalent to 40 seconds for the car to move around this specific oval racetrack, given in terms of that specific illustration. So the first graph is going to assist us in trying to analyze that specific motion for this particular car. And of course, we're going to consider this one from a previous discussion which we have discussed, whereby I mentioned that instantaneous velocity is going to be directed along the tangent path for us to find this specific kind of motion. But its magnitude is going to be different, and it's not equal to the, of course, tangential, or rather, it's not equivalent to this specific, of course, aspect of the slope of this particular curve. So we're going to expect the velocity component at this specific point to be moving along that tangential part to the curve given as that one. And of course, for us to give this specific displacement, we are going to have it given in terms of that straight line from the point A to B given as that one. So for us to evaluate this specific graph, and therefore, perhaps because of our space, I can do away with this. I'm going to have this one given in terms of those specific differences in the x and the y direction given as that one. And this is going to be for the graph of displacement against time. We're going to have the difference delta t and delta s given as that one. Therefore, we can give the velocity of this specific motion for the time frame of delta t given in that specific case, whereby we're going to have the velocity given in terms of delta s over delta t given as that one. So this is going to be from our initial discussion, and therefore we can have as well the concept of average velocity given in terms of still average velocity is equivalent to, of course, this specific velocity component for the x. So in this case, we're going to consider this specific aspect from the previous discussion we have had on vectors, whereby we're going to have this specific velocity given in terms of the x component plus the y component given as that one. So we can just reserve those ones as such. And therefore, this is going to be the velocity component with respect to time given as that one. So in this case, the total displacement, which is delta s, is going to be given as delta s. Now from our vectors, we said that we're going to add this component along the x and the components along to the y to find the resulting vectors for different velocities from my previous statements. So we can split this specific representation and have it as a delta x all over t, which is going to be forming our common denominator. So therefore, we are going to have this one given in terms of this one and delta t, giving us this specific concept of a velocity. Therefore, you can represent this aspect of a velocity as the delta x over delta t is going to represent the velocity component along the x component or the x direction, and the velocity component along the y direction is going to be given by using this second term. So therefore, we can give this specific velocity for a motion in 2 dimensions in terms of the velocity along the x component plus the velocity along the y component given as that one. And this is going to be giving us our representation for the velocity in terms of motion in 2 dimensions given as that one. So in case we have a representation for that one, then therefore we can find instantaneous velocity by having this one given in terms of Vx is equivalent to dx over dt. So this is going to be a general representation from our previous discussion, and as well we can have a velocity component along the y-axis given in this specific representation, whereby x and y are going to be representing the various displacement in those 2 specific directions. So in this case, if we are going to apply these particular concepts which we have described for the 2 case for a car that is moving along that specific curve, and the displacement, of course, in this specific case, we are going to just have to list a few information which we have been given. So we have been told that a car is going to move along this racetrack from point A to B, which is 300 meters. And of course, this specific speed is equivalent to 30 meters per second. And of course, we have been told that the time taken is going to be given as 40 seconds in that specific case. So if we are required to find the instantaneous velocity at the point, of course, 1 and 2, we're going to see that the velocity component, which I've said, which is instantaneous, is tangent to the part of the curve. And basically, it is going to be equivalent to the magnitude of a speed of this specific car. So we are going to see that at the point A, the velocity is going to be directed towards the y component, and therefore it's going to be equivalent. So the velocity along the y component, which is going to be Vy, is equivalent to the value of this velocity, which we have said is 30 meters per second, given as that one. And of course, we're going to see that for a similar case, we're going to find the velocity component along the x given in terms of this specific negative value of negative 30 meters per second given as that one. And from this one, we can evaluate the concept of average velocity. Now, in this case, we're going to see that for us to consider the displacement, this is going to be independent of the path which is going to be taken. So therefore, we're going to consider the magnitude of our displacement from the first place to the last one. And of course, we're going to see that this one can be given as a displacement entirely along the x-axis. And therefore, we are going to have this aspect of displacement along the x-axis given in terms of 300 meters, and this is going to be in the I direction as I've said. And since we have been told that the time taken for this one, delta t, is equivalent to 40 seconds, we can evaluate the specific time taken for this, or rather we can evaluate average speed being given displacement and time using this specific equation, which is equivalent to 300 meters per second divided by 40. So this is going to be 40 seconds basically. So this is going to be 300 meters, not 300. So this is going to be displacement given in terms of 300 meters in the x direction. And this is going to be 40 seconds. So therefore, we're going to have this one given in terms of the values of 7.5 meters per second. So this is going to be the velocity, considering the concept of displacement from 1 to 2, which is going to be along the x, and the time taken given as such. So if we try to consider this is specific velocity, and the one which we were told the car is moving at a constant velocity of 30 meters per second. There's going to be a difference in this specific case, whereby we're going to see that its magnitude is less than the speed of 30 meters per second. And of course, we're going to see that this is due to the fact that the car is going to travel along the curve and not the straight line. So this nature of travel is going to compromise on the specific velocity component, which we have given in terms of the magnitude of course, the displacement and direction given as that one. So we're going to come across several cases whereby we're going to consider this specific nature of course, magnitude and direction, which are going to be affecting the various aspects of velocities and the forces, which we are going to see in our subsequent discussions. So kindly check our description boxes for various links of other videos. Engage us in the comment section and also ring that notification bell to be getting updates on our various discussions in mathematics and sciences. So assume that we have understood how we can evaluate the concept of velocity, and perhaps subsequent videos are going to be showing us the concept of acceleration, which are going to be represented by various vectors, which of course in terms of direction they are going to be affecting the velocity components as I've said given in that specific case. So that is it for now, guys. Bye, God bless you. Catch us in our next video.